So welcome to Math 150, Section 2, 2021, Green's Theorem in a Day, the sequel. So I'm not going to go through everything that was covered in the video. What I want to do is I want to try to emphasize things maybe a little bit differently than that, and then just use this as an opportunity to quickly review a lot of what we've been doing throughout the semester. This is one of the big moments in the course is getting to Green's Theorem. It is usually done in much greater detail in Math 151, where they spend a lot of time doing line integrals, path integrals, and all that stuff. If you want to physics, it is very, very, very valuable to learn how to do stuff like this. There's going to be lots of applications of this in electricity and magnetism and other subjects. For most of you, if you're not really going on into those calculations, it's not something that you're really going to see, but it's nice to know that it exists. And it answers an interesting question. You know the fundamental game of calculus. The integral from a to b of f prime of t dt is big F of b minus big F of b. You don't get the name fundamental. Right? We don't know that many fundamental theorems. So the natural question is, how does the fundamental theorem of calculus generalize? Is there a nice version for functions of several variables and multiple integrals? And Green's theorem, or the generalization of this, the generalized Strokes theorem, is an answer to this. The first is to try to rewrite this. This is the same as integrating over the interval AB of, I'll write it as df, and this is the f evaluated at the boundary of A and B, so this means boundary. Or if you want the integral over the boundary of AB of f. So again, this is, fire hose shooting information. There's a way to view what's going on as integrating the derivative over a region is the same as integrating the function over the boundary of the region. You can almost view the boundary of the region as almost like the derivative of the region itself. So the generalized version is the integral of some form df over omega is the integral of f over the boundary of omega. We will look at a very special case of doing integrals in plane, but this is just one of many, many steps. Okay, so what's going on? We need to talk a little bit about the types of integrals we can do. And so we've talked a little bit about how to integrate along a curve. And so we did this to find what is the length of a curve. So we have some curve in space. And what we did is we chopped it up into lots of small pieces. And the hope is that as you chop it up into more and more pieces, that adding their lengths will basically give you the whole length of the curve. And we found the lengths of these by using the mean value theorem and looking at gamma prime, and by looking at the definition, looking at the definition of derivative. So let's say we have some curve here, T. Maybe this is x of t, y of t. If we're in two-dimensional space, if we're in three-dimensional space, obviously there would be a z of t. Sometimes it's easy to view, or better to view, a curve in the plane as actually being less in three-dimensional space and just having zero what's there from home. And so we want to look at c prime of t, which would be x prime of t, y prime of t. And so the first integral we often wanted to do was integrate, and we'll call this curve gamma, integrate along some curve gamma of the function f. And by this we'll mean t goes from A to B of f of c of t, and then the length of c prime of t at. So this would be integrating a function f along the curve. And in the special case when f is 1, we would just recover the length of the curve. We could have a more interesting integral. And we could have maybe some vector F that we're integrating along the curve. So how many of you are taking physics? Okay, so basically this lecture is going to be more geared towards the two of you today. I remember when I was a sophomore, I was visiting a friend of mine who was a freshman at Harvard, and I went to her multivariable calculus class. And when we left, I was talking with friends and with friends about what a great lecture it was. And they're all looking at me, go, it was wonderful. Wasn't it great how the professor explained how all this connects to physics? We go, yeah, we entered the class thinking we don't know math, and we left thinking we don't know math, and we don't know physics. And so there's a danger of trying to motivate while at the same time, if you haven't seen the motivation, it can just become frustrating. And you absolutely realize that if you're not doing physics, some of this is not going to seem as relevant. But we only have one lecture devoted to this, so it's a small amount of time. For those of you who are going on in physics, it is worth seeing. For those of you who are not, it's worth getting a sense of what are the motivations, what is the inspiration for quantities like this. So when you've done some problems in physics, you often ask what work is done moving a particle along the trajectory. And all that really matters is the direction of the force tangent to the curve. And so what you come up with is you study the integrals of f divided with ds. Is you care only about the component of the force in the direction that you're moving along the curve. And so what we would want is the integral along gamma of f dot ds, and I'm putting the atoms to remind myself that this is vector value. This would be the integral t goes from a to b of f of c of t divided with c prime of t dt. So very similar to what we had before, except now we're doing jump files. All right, so these are integrals that we can try to do. And now we need to figure out what's a good shape to study. So we often like to study non-intersecting closed curves. So what do you think a closed curve would be? If I start here, what should happen? Should come back here. And since it's not intersecting, I don't cross myself along the way. If I give you a beautiful figure 8 or slightly deformed figure 8, I could do this as two curves. And then each one would be non-intersecting. And so the general idea is you reduce a complicated quantity to a bunch of simple ones. So we will often do integrals over non-intersecting closed curves. If you had to choose a curve or a region, what would you choose? Circle is one of the two candidates. Square or rectangle. So these are the two choices we have. Which would you rather have? Integrals over squares or rectangles, or integrals over circles? Probably rectangles. Rectangles fit together nicely. If you catch them together, they make super rectangles. Circles don't fit together as nicely. But circles are very good for a lot of things. They parameterize nicely. There's a lot of good things about circles. So we will mostly study a curve like this. And when we're traveling a curve, we have to decide, do we want to walk clockwise or counterclockwise? And the convention is to do clockwise. Does it matter? No, but you don't want to use a different convention than everyone else. Is anybody here a potential econ major? Okay. What have I just drawn? Supply and demand. And what is the axis down here? What's the horizontal axis? Quantity. And over here, price. And so as price increases, you're willing to supply more. And people typically buy less. You have different goods where that's not the case. Could you have price on the horizontal axis and quantity on the vertical? Of course. Economics won't change, but you will be using the opposite convention of everyone else, and you will almost surely cause some confusion. So it's just a convention. The convention is we choose to walk counterclockwise. When we did our cross products, we chose to use the right-hand screw rule in terms of we're having V move into W with our fingers curling like this and the thumb pointing in the direction of what the cross product is. So if this is a point AC over here, and this is the point BD, and this be BC over here, this would be AD over here, and I'll break this up, I'll call this 1, 2, 3, and so my curve is going to have 4 points. Now, when you're looking at integrals like this, I have some physical curve gamma in space. And I want to show that the integral doesn't depend on how I parameterize the curve. That if I choose a different parameterization that matches this physically in space, I get the same value. And it's just a calculation you need to do in the All right, so let's try to interpret what is f dot ds. So I want to calculate what's going on over here. Well, if I look at c prime of t, c prime of t is x prime of t, y prime of t. I claim one of those quantities is particularly nice along segment 1. Is it x prime of t or y prime of t that's nice along segment 1? Y prime of t. So what is y prime of t along segment 1? 0. And similarly, y prime is 0 along segment 3. On segment 2 and 4, what's going to be 0? X prime of t. So when we look at the integral of f dot ds over something like this, let's say f is equal to p comma q. Then the integral over gamma of f dot ds, I can view this as the integral of p dx plus q dy. For our rectangle here. Sometimes people put a little circle on the integral. Looks cooler. It also means that it's a closed curve, so that you can quickly look at this and see it's a closed curve. I can just write it like this because I know when I look at the dot product of f, which is pq, with c prime, which is x prime of t, y prime of t, well, I've got p x prime of t dt, q y prime of t dt. Well, on this segment, dy is 0, and on this segment, dx is 0. So there's no contribution for the integral of p dx along sections 2 and 4. Similarly, for q dy, I can really view this as this is integrating p over 1 and 3, and this is integrating q over 2 and 4. The other integrals are just going to be true. The beautiful Stokes theorem, or Green's theorem, says that this is the integral of dq dx minus dp dy dx dy. Or, more generally, the integral over gamma of f dot ds is the double integral of the curl of f dotted with dA. And the way we calculate the curl is you can use the mnemonic I, j, I hat, j hat, k hat, d by dx, d by dy, d by dz, p, q, r. So this is just a mnemonic to remember what is the del cross of vector. So the I component would be d by dy epsilon r minus d by dz epsilon, and so on and so on. If we're in the special case when r equals 0 and p and q just depend on x and y, this turns out to become just dq dx minus dp dy in the k direction. And then everything is going to work out very nice. All right, so this is the Green's. So we want to prove when you look at this, you've got an integral of p dx and an integral of q dy, and you have a double integral of dq dx and a double integral of dp dy. What do you think the integral of p p dx might equal. So if this is true, if this left-hand side equals the right-hand side, what do you think the integral of p dx equals? So we know these two together are the same as the integral of these two together. Do you have any thoughts of what just the integral of p dx equals by itself? So imagine I change q a little bit. If I change q a little bit, can I change the integral of p dx if I just change q? If I change q, does that change the integral of p dx? On the right-hand side, if I change q, does it change the integral of dp dy? If I just changed q. No. So what does the integral of p dx have to equal? The integral of p dx has to equal what part of the right-hand side? The integral of dp dy. Because they're independent. I can change q over here, and that can't affect the dp dy term over there. So the integral of p dx has to be the double integral of dp dy. So this is an incredible observation, and I don't think I made this 8 years ago. That when we're looking at this, we know that we have to be matching terms this way. We have to match the p dx with the double integral of dp dy. Which would you rather show, that the p is equal or the q is equal? The proofs are similar. One of them is slightly better algebraic. Not very much, just a little. Any preference? Yeah, why q? It doesn't have the minus sign. So I would much rather do the q, which has no minus sign. Absolutely. Now, when you look at this, dq dx and dp dy, they're both area integrals. For dq dx, which would you rather integrate first, with respect to x or with respect to y?
Y.
So you have dq dx. Okay? So we have dq dx. You either have to give me a function whose derivative with respect, I want an antiderivative with respect to x, or an antiderivative with respect to y. If I want an antiderivative with respect to x, this means give me a function whose derivative with respect to x is dq dx. If I do it the other way, give me a function whose derivative with respect to y is dq dx. Which would you rather have? Would you rather integrate with respect to x and find a function whose derivative with respect to x is dq dx? Or would you rather integrate with respect to y and find a function whose derivative with respect to y is dq dx? Yeah, with respect to x, you've got this as d by dx of q. So because we're taking the partial with respect to x, I'd love to integrate with respect to x and just remove that. For the dp dy, would you rather integrate first with respect to y or with respect to x? Without any dy. So the claim is the integral of p dx. Oh, sorry, I'm doing q. Dy. The integral of q dy is equal to the double integral of dq dx dx dy. And so we'll use, if necessary, convenience theorem to do them in the right order to make our life easy. All right, so let's try to analyze the double integral first. So let's write it out very slowly. So this is the same as the integral y goes from c to b, integral x goes from a to b, dq dx dx dy. So I need a function whose derivative with respect to x is the derivative of q with respect to x. Okay, that's not so bad. So I have y goes from c to d, and then I just have my function q at x, y, and then I evaluate it at x equals a and b, dy. Okay, so continuing to write the template, what do I have? I have an integral y goes from c to d, and I'll have q. So I first put x equals b, so I'll have b comma y minus q of a comma y dy. So I really have two integrals. I have q of b comma y goes from c to d. So when I look at my square, where is this integral from y goes from c to d of the function q of dy? Is it 1, 2, 3, or 4? So I'm telling you the x coordinate is always b, and y ranges from c to d. It's just here, that line of x equals b, and since y goes from c to d, we're just going up. So this part over here is just the integral a3 over 2. Now let's look at the next one. We have negative integral of q of ay. So which region is that? 1, 2, 3, or 4? 4. 4. Which way are we integrating 4? Well, we're having y go from c to d. So we're going in the opposite direction as we're supposed to. But the negative sign here reverses that. So if you take the negative of an integral, that's the same as flipping the order of integration. So really, I can write this as this is equal to the integral y goes from c to d of q of dy plus the integral y goes from d to c of q of ay dy. And now that's just the integral of q over 2 and the integral over 4. And now I'm going in the correct direction. I don't have the integral of q over 2 and the integral of q over, the integral of q over 1 and the integral of q over 3. But what's the integral of q over 1? So I'm integrating q dy. What's the integral of q dy over 1? So what's the integral of q dy over 1? What do we know about dy on segment 1? It's 0. So what's the integral of q dy on segment 1? It's just 0. What's the integral of q dy over segment 3? So 0, because dy equals 0. So this is the same as the integral of q dy. And it was precisely what we wanted to show. So this proves the integral of q dy is the double integral of dq dx. And now all we have to do is show something very similar for the integral of p dx and the double integral of dp dy. So this is a question.
Yeah. So does it just end up everything being 0 then, since everything cancels out?
No. It's just the integrals of q dy over 1 and 3 are 0. But the integral of q dy over 2 and 4 need not be 0. So what we're really saying is this is the integral over 1 of q dy plus the integral over 2 of q dy plus the integral over 3 of q dy plus the integral over 4 of q dy. And when I write it like that, it's just this piece here is 0 and this piece here is 0. So we can just add those back. So the only pieces that contribute potentially are the 2 and 4. So this is Green's theorem for a rectangle. We will see later how to extend from a rectangle to other shapes. But first, let's test Green's theorem, and let's try looking at an example. So we need a curve that we can integrate over and we can parameterize easily. Anybody have any thoughts about what might be a good curve to look at? Circle. So now we're going to use the circle. So we can write down the equation of the circle without too much trouble. And so let's do a unit circle. So let's say C of t is cosine t sine of t, 0 plus equal to t plus equal to 2 pi. So we'll have a circle. Are we going through the circle clockwise or counterclockwise? So when t equals 0, we start here at the point 1, 0. And as t increases, we go up and we go down. We go up. So we've at least parameterized it correctly. Okay. C prime of t is going to be minus sine of t cosine of t. It feels like forever since we've taken a derivative. Now we need to choose the function. I can choose any function I want. I will choose the function negative y comma x. Do you think this is a completely random choice? No, of course not. Right? This is probably chosen deliberately. Now, there are certain integrals that are going to be extremely nice and easy to do. What would you love to be true about? This is called the curl of f. If the curl of f could have be anything, what would you want the curl of f to be? The curl of f is del cross f. It's dq dx minus dp dy. What would you love that to be? I'm going to make the integral really simple. Simplest value. 0. Right? If the curl of f is identically 0, what's this integral to be? 0. And if you've done physics, if you hear things about conservative forces, do no work along a closed path, that's where you're getting stuff like this one. The corresponding line integral within be 0. So if the curl of f is 0, no work is done, and this integral is just 0. Conversely, if the integral of f dot ds is 0, f is always perpendicular to motion. So imagine you're moving in a circular orbit about the sun under gravity, then this integral will always be 0. And you can then use that to actually deduce maybe things that maybe the curl is. And there's lots of questions you can ask them back and forth. So the simplest thing for us is if the curl is 0, then we can do these integrals. What often happens in classes where they do a lot more on line integrals and path integrals is early in the semester, they give you problems where the curl is 0 or the curl is something nice, and they have you do the line integral as homework problem, and then the professors and the graders know that they can quickly check the answer by using GreensThm. So the idea is this is a new way of doing integration, that sometimes rather than doing the initial line integral, it might be easier to convert this to an area integral. So almost surely this is not a random choice of negative y comma x. We'll see surely that this is a terrific choice. If I look at f of c of t, this is f of x of t, y of t, right? No. That's the same as f of cosine of t, sine of t. And so f of xy is negative yx, so this is going to be negative sine of t cosine of t. Right? Let's continue to calculate. So f of c of t dotted with c prime of t. So we have negative sine of t times negative sine of t is sine squared of t, plus cosine of t times cosine of t, cosine squared of t. It's going to be sine squared of t plus cosine squared of t, and that is 1. So we get the integral along gamma of f dot df, and by that we mean the integral that t goes from 0 to 1 of f of c of t out of c comma t dt is the integral from 0 to 1 of 1, I'm sorry, 0 to 2 pi. So we need to go from 0 to 2 pi of 1 dt, and what is that integral? That's just going to be 2 pi. All right, so the line integral was pretty easy to do in this case. Let's look at the area integral. So we want the curl of f. That's going to be dq dx minus dq dy. All right. What's the partial? So here, this is my p comma q. So q of xy is just x. P of xy is just negative y. So what is the partial of q with respect to x? Q of xy equals x. P of xy is negative y. So dq dx equals 1. And then what is dq dy? Negative 1. So you get 1 minus negative 1, which is 2. So now, if you look at the integral of the curl of f dA, this is the integral of dq dx minus dq dy, dx dy is the integral of 2 dx dy over the unit circle. How can I view integrating 2 over the unit circle? What does that equal? So what would this integral be? If you integrate 1 over a region, what would you get if you integrate 1 over a region? Can you do that double integral? Just the area. So what would you get if you integrate 2 over a region? 2 times the area. So this is just 2 times the area of the unit circle. Oh, well, if 2 times the area of the unit circle is 2 pi, and you get the area equals pi. We have just found a new way to calculate areas of objects. If you can do a corresponding line integral, you can actually get the area. It now comes down to when are you able to do the corresponding line integral. If you can't do the corresponding line integral, it doesn't matter that you have this connection. But if we take the function negative y comma x, the curl of that, dq dx minus dq dy, is just 2. I could have been a little fancier, and I could have taken negative y over 2 x over 2, so that it would have just come out to be the area, not twice the area. So this hopefully gives you, some sense of the power of GreensThm. That we are able to use this to compute to compute areas. Okay. Any questions about this example? Okay, so for the last few minutes, I want to just talk a little bit about how you would try to prove GreensThm in general, and how you might try to use it when things go wrong, and what happens if some of the conditions don't work. Can I erase this all? I want to try to keep the statement of GreensThm up as long as possible. So right now, we only know GreensThm for a rectangle. Fortunately, rectangles fit together very nicely. And so you can pass from knowledge of GreensThm on a rectangle to knowledge in general. And the argument goes something like this. So imagine you have some region like this. So you just start slicing slicing it into a rectangular grid. And let's look at what goes on in each one of these squares. So in this square, I apply Green's theorem, and the integral along the boundary is equal to the double integral of the curve. Now I go to the square one to the right, and I apply Green's theorem on that. And what do you notice about these two adjacent rectangles? What happens?
Goes up and down.
Yeah, and so what happens to this up and down? They cancel. And if I continue to go over here, if I come down over here, what you see is every interior wall is traversed twice in opposite directions. So all the interior walls cancel. And what happens is you start expanding out and you get the curl of FM over the whole region. If your outside curve is rectilinear, it's something like this. Then you'd be done. Because we can always expand outward to get something like this. If it's not rectilinear, if it's slightly curved, we have a small problem now. So what you can do is you can try to zoom in and approximate it. And you can take a rectilinear path that's getting closer and closer and closer. We have to be careful because we saw a while ago that if we're a little bit too cavalier, we would get that every curve has the same length. Because we can drop all the horizontals down, we can push all the verticals over, and then it doesn't matter what curve you have, it's just going to be the horizontal length plus the vertical. So it's extremely important that we have a dot product going on. That we are being careful. We're not saying the length of this is the sum of those lengths. We're using slightly different items. And so this can be made rigorous, and you can show that, yes, if you take a smaller and smaller mesh, this converges. If you think about this, if I have a curve like this, I could approximate this with a rectilinear curve, maybe with indentations of size 10 to the negative 4 billion. You're well below Planck's scale. And for all practical purposes, it would look smooth, but it really is rectilinear on a fundamental level. And the hope is that if you go down that far, the error that you're making is really minuscule in terms of what's going on. So this is the idea of how you would take what's going on for a rectangle and expand it out. If you have something like this, you're fine. If you're looking at the area integral, these regions over here in the limit are going to have extremely small area, even when we put them all together. And so pushing out the integral of dq dx minus dp dy to include these small little bits is not a problem at all. The problem is the integral of f dot dx. So that's one item. The next thing that I want to mention is imagine I give you a curve like this. So as always, you travel through it counterclockwise. And I tell you the curl of f is 0. What do you know about the integral of the curl of f over this region? 0, right? What if it's 0 except at one point where f blows up? So can anyone give me an example of a function that blows up at one point? Anybody know a force that blows up at a point? If I had my lunch here, I might throw a piece of fruit at it. Might be an apple.
Gravity?
Gravity, right? What is the force of gravity? Classically, gravity is 1 over r squared. The force between two objects is inversely proportional to the square of the distance between them. It blows up. Well, since you can't have two objects in the same place, that's okay. But if we're trying to look at what's going on, we have a singularity. Gravity is blowing up at 1 over r squared.
Well, wouldn't it be like increasing leading up to that too?
It would, but leading up to it, everything is fine. It's just at that point that it goes haywire. And the question is, what are the consequences of being bad at just one point? We've seen with polar coordinates that sometimes there's not a unique theta for every x and y, but it's only one point, the origin, where it breaks down, and that's not such a big deal. So over here, what is the problem if it breaks down at one point, and this one point we have a singularity? The beautiful idea is the following. Let's draw, not to scale, a small circle of radius epsilon above this. I'll call that c sub epsilon. And what I'm going to do is make a little slit. I'm going to come here, I'm going to go to the circle, I'll travel the circle counterclockwise, and then I'll come back. And maybe I'll make the thickness over here itself. If you look at this, is this now a nice simple closed curve? Yeah. And it's a simple closed curve, and the curl of f is 0. So what must be true about the line integral over this closed curve? It's 0. It's 0 for every delta. So we take the limit as delta goes to 0. And the limit as delta goes to 0, the slit converges, and now these two are going to be going over each other in opposite directions, so they cancel. And so what happens in the limit as delta goes to 0 is you have the integral over the outside curve plus the integral over the inside curve going backwards, going in the wrong direction, equals 0. So the limit as delta goes to 0, the integral, I will write it as, we'll call this curve gamma. So delta to mean I'm missing that small little part here, plus, we'll call that maybe delta 1, minus c epsilon, because we're going through c epsilon in the wrong order, plus delta 2 of f dot ds equals 0. And as delta goes to 0, this just becomes the curve gamma. Delta 1 and delta 2 cancel each other out. And then we're just left with negative c epsilon. So we get the integral over gamma of f dot ds equals the integral over c epsilon of f dot ds. Because if the integral over gamma plus this in the wrong direction equals 0, then the integral over this equals negative the integral of this in the wrong direction. And the negative of the integral in the wrong direction is just the integral in the right direction. If we restore the sign, we move it over.
What do you get from that?
What we get is that if I have a function whose curl is 0 everywhere except one point, I can say the line integral along the boundary is the same as the integral over a circle of radius epsilon centered at that one dot point. And what this allows us to do is if you have a function that is nice everywhere except at one point where it has a singularity, you can say, my line integral is equivalent to just integrating over a circle of any size radius. And you reduce doing complicated integrals like this to simple ones. So the whole point of this is that you only have to now study certain integrals. And of course, if you can do something once, you can usually do it finitely many times. So if I have a region like this, but I have 3 points where it blows up, what I can do is I can draw small circles about each one of them. And you can play the split game first with each one of them, down and back, down and back, down and back. And you get that the integral over the outside boundary curve would be the integral over 3 little circles, one about each point where it blows up. And this is one of the real powers of GreensThm, allows you to reduce challenging computations to simple. You look a little.
Yeah, it just seems to me like I don't like when would you use that? Well, like what would be a case where you want to do that?
So it turns out when you're trying to understand, say, work done by certain forces, this allows you to figure out what's happening from like a point source charge. And in complex analysis, this idea of replacing line integrals with integrals over little circles is used all the time. And in fact, you can reduce a lot of integration theory to just finding Taylor series. And it turns out in complex analysis, the only term that matters in the Taylor series is that it's actually a more general Taylor series. It includes not just x squared, x cubed, but also x to the negative 1, x to the negative 2, x to the negative 3. And it turns out that Green's theorem allows you to handle a lot of integrals by reducing it to finding the negative first Taylor coefficient of a lot of functions. So I am going to be giving a lecture to some of my summer students about this on Thursday. I will send the link in case anybody is interested. I will also just make that lecture available to you in complex analysis in a day. But it allows you to evaluate a lot of very difficult integrals. And so just, it's a good question, and I'm trying to answer it honestly and not just say, well, if you go to graduate school, you see it then. I can give you a nice, integral from minus infinity to infinity. And I want to evaluate this. And the way you can evaluate this is, screw that. Let me go from minus r to r, and I just take the limit as r goes to infinity, and that gives me an integral from negative infinity to infinity. And what I'm going to do is I'm going to take this and I'm going to close the curve. And I'm going to make a closed curve like this. And imagine that when you close the curve, the integral of your function along the top becomes very, very small because you have large decay on the top. And imagine your function happens to have a singularity right over here. You can then say that the integral over this region is the same as a simple integral of a small circle over there. And it allows you to evaluate a lot of integrals from minus r to r by just doing, instead, a very simple integral about a point over here. So it turns out that Green's theorem is tremendously powerful for complex analysis, where an analog of this lives, and it allows you to say, well, if I have this one segment over here, I can often complete it and make a closed curve. And often when I complete it, maybe I'm integrating the function e to the negative x plus iy 1 over x plus iy squared. Well, I can switch the full column. So when I look at what's going on, let's just do what's going to have like 1 over z to the 4. If I want to try to calculate what's going on along this curve over here, this is so far out that every point over here is going to be r units from the origin. So z to the 4th absolute value is just 1 over r to the 4th. The length of this segment is 2 pi r. So the contribution from integrating this over this curve over here would be something of size 1 over r cubed, which is tending to 0. And so it turns out that there's a lot of functions you can look at where when you complete them like this, the integral over the top, you're essentially adding 0 in the limit. And so the integral that you want over here, plus something that tends to 0, is the same as an integral of a small little circle. And those small little circle integrals can be done very easily. And so this is one of the reasons we really care about this, is a lot of integrals that we cannot evaluate any other way, we can now evaluate. It's important to note that we are not finding antiderivatives. We're only finding things like integrating from minus infinity to infinity. Big integrals like that we can do. but we still can't find anti-derivatives of simple things. All right, so Friday's class is going to be a review. And so anything you want is get your task. If you do not want to come, perfectly fine, it's an optional class. And then the last exam will be Monday and Tuesday. Remember that part 1 is due at the start of class on Monday.